will go for exclusive analysis of transverse electric wave. As I said, for the transverse electric wave, there will be no electric field component in the direction of z, that the electric field component is always perpendicular to the direction of z if the wave is travelling in z direction. So, in our example, we are assuming that the rectangular waveguide is placed along z direction and the wave is travelling in z direction. Therefore, there will be no field component along z direction for transverse electric wave. So, whenever we are considering a transverse electric wave, what is the condition we are supposed to take? Remember this condition, that Ez is equals to 0, that the transverse electric wave will have 0 electric field in the direction of wave propagation, that is Ez is equals to 0. What about the Hz? Hz is not equals to 0. That clearly you are supposed to substitute these two in our already obtained equations for Ex, Ey, Hx and Hy. So what I do is just I will substitute these two conditions. Now substitute them. If you are substituting, Ez is equals to 0 corresponds to this term will be vanished, this term will be vanished, this term will be vanished and this term will be vanished. After vanishing those terms, substitute Hz equation here. Here substitute Hz, substitute Hz, substitute Hz, substitute Hz and differentiate that one, get the final equations. So directly I will try to write down the final equations for that one. From this one, after vanishing the first term as Ez is equals to 0, the remaining term is minus j omega mu by h square dou by dou y of. So what is solution? Obtained solution for Hz, some constant C cos m pi by ax cos n pi by by e power j omega t minus gamma z. So directly what I am doing is I am writing the equation. So without Ez is equals to 0. Now if you are differentiating that one with respect to y, only this term will becomes minus sign, a negative sign n pi by b, and the internal multiplication of that one will becomes n pi by b will be the multiplication factor for this one. So that is the final equation for Ex. Clearly observe that, that's not writing that equation, so you can differentiate that one. Similarly, you will get equation for Ey as Ez is equals to 0, the remaining term which is left for us is j omega mu by h square. Directly I will try to write down the differentiation equation here. The differentiation is with respect to x, so the x factor will remains for us c m pi by a, and this will becomes a negative sign, so I am adding a negative sign in front of this one, sin m pi by a x, the cos term left as it is, n pi by b y e power j omega t minus gamma z. So this is the final equation that what we have for our Ey, right? Similarly, what will be the final equation for Hx? For Hx, substitute Ez is equals to 0. As Ez is 0, this term will be vanished and this term remains for us. I am trying to write down this entire term directly. This differentiation is with respect to x. Since this differentiation is with respect to x, the similar term remains for us, that is m pi by a, and this will be negative sign, a negative of negative, plus will be added here, sin m pi by ax cos n pi by by e power j omega t minus gamma z. That is the final equation for our Hx. So this is final equation for Hx. As Ez tends to 0, the remaining term remains for us. Now for Hy, this term will be vanished, and instead of Hz I am substituting the equation, and after that one what I get is minus gamma by h square. This is with respect to y, so what I get is c n pi by b, that the y term is n pi by b left for us, and cos here the negative sign will becomes positive, n pi by b, this is sin n pi by b y cos m pi by a x, just it was swapped, e power j omega t minus gamma z. This is the term which is left for us, right? So here clearly examine once again, if there is any sign disturbance, just you correct it. That clearly what I am doing is I am substituting this Ez is equals to 0. Ez equals to 0 corresponds to this term will be vanished, this term will be vanished, this term will be vanished and this term will be vanished. After that one, substitute Hz here, here, here and here. Differentiate that one. After differentiation, this equation also will be modified. Now what I do is just I will try to modify this equation by eliminating this particular differentiation term. What I do is just I will eliminate this differentiation term instead of this one. So this differentiation is with respect to y, right? So this term will now becomes sin n pi by b y multiplied with n pi by b. So that is the final solution. Directly I wrote the final solution there. Now these are the 4 equations that what we have for a transverse electric wave. For the transverse electric wave, once again clearly remember that Ex, Ey, Hx, Hy and Hz will remains for us. There will be no Ez component. The Ez component is always 0 for that one. After making Ez 0 and substituting Hz, these are the 4 components that which are left for us. Now using those 4 components, we are supposed to analyze what are different waves we can exist, different modes we can observe for transverse electric wave. So what are different modes? The mode is purely depend upon how many half wave variations are there in our rectangular waveguide along broader dimension, along narrower dimension. So half wave variation means how many part signals are there along the broader dimension, how many part signals are there along the narrower dimension. This will be described using a mode called as TE with suffix M and N. So the mode will be described as TEM N. This is called as the simple mode notation. Transverse electric wave, half wave variations along broader dimension, half wave variations along narrower dimension. By varying different values of these M and N, we are supposed to observe whether the wave is existing or not initially. After existing that one, we are supposed to observe different equations or different parameters for that one. So what I do is just I will go for existence of the wave for different modes. Whether it is existing or not, we will examine, right? Starting from 0, 0. That clearly remember this TEMN is the general notation that what we have. What I do is I will take these 4 equations. I will analyze these 4 equations for different values of M and N. They are called as the modes and start with TE1, TE00. Initially it is TE00. That put M is equals to 0 and N equals to 0. If you are substituting M equals to 0 and N equals to 0, put M equals to 0 here and N equals to 0 here, what you will get is 0. M into 0, N is 0, what you will get is 0. M0, N0, 0. M0, N0, 0. So after substituting M equals to 0 and N equals to 0, we are not getting any of these 4 field components. Ex is 0, Ey is 0, Ez is 0 and Hx is 0, Hy is also equals to 0. Therefore, clearly you can say that Ex is equals to Ey is equals to Hx is equals to Hy is equals to 0. As we are not getting any of these field components, simply what you can say is this particular mode does not exist. That is not at all possible to transmit a wave with this particular mode in our rectangular waveguide. That's what you are supposed to remember. Next, we will observe the second type of mode. Let us consider TE01. That I am substituting M is equals to 0 and N equals to 1. 0, 1 stands for M is 0, N is 1. Substitute M is equals to 0. If you are substituting M is equals to 0, sin 0, this term will be vanished. That is corresponding one Ey term will be vanished. M is equals to 0, sin M, this term also will be vanished. So Ey and Hx terms will be vanished. So clearly what you can say is Ey is equals to Hx is equals to 0. But don't leave there, just examine the remaining 2 components also. M is equals to 0. If you put M is equals to 0, this term will exist for us. It is not vanishing. Definitely it is existing. That is Ex is existing. Similarly, Hy, if you put M is equals to 0, this is also existing. As N is equals to 1, just I am ignoring that one. Just you put M is equals to 0, then Ex and Hy are existing. That what I am writing here. Ex is not equals to 0. Hy is also not equals to 0. So whenever we are saying that electromagnetic wave is traveling in TE01 mode in a rectangular waveguide, these 2 are the field components which are existing. Only Ex and Hy will exist. That you may be asked a question like this. For a transverse electric wave traveling in a rectangular waveguide with so and so dimensions in TE01 mode, which of the following fields will exist? Ex, Hx, Ex, Hy, Hx, Ey and Hx, Hy, Ey. Like that, different options will be given. So clearly you are supposed to recollect that only Ex and Hy will remain, the remaining field components will become 0. Next, observe the third mode or the next mode, TE10. For the TE10, I am making m is equals to 1 and n is equals to 0. Put m equals to 1 and n is equals to 0. As m equals to 1, leave it, put n is equals to 0. If you are substituting n is equals to 0, this term will be vanished. That Ex is equals to 0. N is equals to 0 corresponds to, there is no variation in this one. You will get 1 here, but this entire term will exist for us. That this n is equals to 0. Here also this will exist for us, right? And n is equals to 0. This term will be vanished. So this term will be vanished, this will exist, and this will be vanished. So the corresponding two terms Ey and Hx will exist. That what you can write here is Ey is not equals to 0 and the Hx component is also not equals to 0. The remaining two field components Ex is equals to Hy is equals to 0. So clearly remember once again, the statement may be like this or the question may be like this. Which of the field components will exist for a TE10 mode when it is traveling in a rectangular waveguide? Ex, Hx, Ex, Hy, Hx, Ey, Hy, Ey. Then clearly you are supposed to say that Ey and Hx will exist for us. The Ex and Hy will become now 0. Like this, different field components will be there. And we will examine one more mode also. That is TE11. For this TE11, clearly m is equals to 1, n equals to 1 will give you all these four field components. So nothing will vanish here, right? If you substitute m equals to 1, n equals to 1, this will exist, this will exist, this will exist, and this also will exist. So all field components will exist for us. Like this, depend upon the constants m and n. How many half wave variations are there along the broader and narrower dimensions, the wave propagation will be decided. So if you are saying that simply the transverse electric wave, that's wrong. It's a transverse electric wave in which mode it is traveling? It is traveling in 0-1 mode, 1-0 mode, 1-1 mode or the higher modes. Clearly we can say that T00 mode does not exist on a rectangular waveguide. So if you want to draw how the wave variations will be there in a rectangular waveguide, you are supposed to observe what are the field components which are existing here. What I do is just I will try to draw T01 wave for rectangular waveguide. For T01, what I do is just I will draw, let us take for this one, this is the rectangular waveguide that what we have. For this rectangular waveguide, how the wave variations will be there? If you want to imagine, you have to imagine like this. What are the field components which are existing for us? Ex is existing, that is the electric field in x direction is existing. Hy is existing, the magnetic field in y direction is existing, right? The electric field is in x direction, that is along the broader dimension it is 0, along the narrower dimension it is existing, that is along the narrower dimension the electric field is existing like this. That solid line always indicates that the electric field is there. The electric field is existing in which direction? X direction, that is along the narrower dimension. Around this one the magnetic field will be there. What is the direction of magnetic field? The magnetic field direction is only y direction. So the magnetic field will be like this. It is coming out like this and going into here, coming out like this and going into here. Just clearly the H field will be like this and E field will be like this. This is a way of drawing the fields in a rectangular waveguide. Similarly, if you are considering TE10, how to draw the TE10? How many half wave variations are there in our broader dimension? One half wave variation will be there. That half wave variation is existing in which direction? Y direction. So if you are drawing for this one, this is the rectangular waveguide that what we have. Let us consider this is the rectangular waveguide. The field component which is existing is in y direction. That this is the electric field component which is existing in y direction. Now what will be the magnetic field? Clearly the magnetic field is like this. So this is coming out of the plane and it is going into the plane, and that magnetic field is along x direction. So clearly you have to interpret how a particular wave is transmitting depend upon its mode. These are the different modes, and based on these modes how it is traveling for a particular mode in rectangular waveguide, and so you need to interpret like that. Now we will go for further analysis of our rectangular waveguides. What is the cutoff frequency, what is the cutoff wavelength, and further analysis. Now we will discuss about cutoff frequency of our rectangular waveguide. As we said, once again recollect that it is a high pass filter, definitely some cutoff frequency will be there. Now I will give you the equation for that cutoff frequency. A very simple derivation is there. We will discuss about cutoff frequency. As we said, the waveguide, rectangular waveguide, it's not only rectangular, every waveguide will act as a high pass filter. Definitely there will be some cutoff frequency. A simple derivation is there, just you observe that one. We have one simple relation that h square is equals to gamma square plus omega square mu epsilon, right? Which is equals to, already we defined this one as a square plus b square. After getting the solution for that one, a and b, this will be equated to m pi by a whole square plus n pi by b whole square. Now what I do is just I will take these two equations and I will try to modify it. Then obtain gamma square. Gamma square is equals to m pi by a whole square plus n pi by b whole square minus omega square mu epsilon. Now gamma is equals to, simply from this one gamma you can write this one as gamma equals to square root of this entire term, that is m pi by a whole square plus n pi by b whole square minus omega square mu epsilon. But what is gamma here? Gamma is clearly the propagation constant. The propagation constant is a combination of attenuation factor alpha and phase constant beta. So this gamma can be written as alpha plus j beta. Now examine this particular term. If you are examining this one, this will be taken as the entire a similar term, and this will be clearly related to the frequency. For lower frequencies, if the frequency is very less, omega square mu epsilon is less than this particular one. That is clearly for a lower frequencies, this omega square mu epsilon is small. For small values, this entire term becomes positive, right? This entire term positive means the solution is also a positive quantity, real quantity, that what you can say. If it is real, simply what you can say is only alpha exists. There will be no beta term here. Once again, observe the condition. For lower frequencies, this omega square mu epsilon is a small quantity, less value. Since it is less than this one, definitely the quantity what we are getting is a real quantity. Since it is real, in the solution the real quantity is only alpha. That alpha only exists, the attenuation only exists, there will be no phase constant. Therefore, completely the wave will be attenuated. That's what you can say. If there is such scenario, then this particular wave is called as evanescent mode. That this evanescent mode will have no propagation of the wave. And if for higher frequencies, if you are considering the very large frequencies, if frequency is more, then this omega square mu epsilon term is larger than this term. If it is larger than this term, definitely in the square root what you will get is a negative quantity. Then obviously both this real quantity as well as the imaginary term you will get. That the quantity gamma is imaginary, right? If it is imaginary, both alpha and beta will exist. If alpha and beta will exist, definitely the wave will propagate. This is called as propagation mode. So whenever for lower frequencies we are observing this one, evanescent mode will, there is no wave will be there. For alpha and beta both are existing, that is at high frequencies, it is called as propagation mode. So at which frequency it is shifting from evanescent mode to the propagation mode, that particular frequency is called as the cutoff frequency. That cutoff frequency will exist exactly at these two terms equal. That if you are making these two terms equal, that particular frequency is said to be the cutoff frequency. So make them equal. That is omega square mu epsilon is equals to, what is the term there? M pi by a whole square plus n pi by b whole square. This omega c is nothing but the cutoff angular frequency. That's why I'll represent that one with cutoff W or omega c. Now with this relation you will get Fc also. So for that I will get just Fc from this one. Now from this equation clearly you can observe that omega c square is equals to 1 by mu epsilon multiplied with this m pi by a whole square plus n pi by b whole square. Now omega c can be simply, if you are writing omega c, put a square root here, then that will be the modification, right? Omega c is equals to 2 pi fc. Therefore fc can be directly written as fc is equals to 1 by 2 pi square root of 1 by mu epsilon square root of m pi by a whole square plus n pi by b whole square. Now what is 1 by square root of mu epsilon? Velocity of the wave in that particular medium. If the medium what we are considering between the walls is air, then simply it is said to be the or light velocity c. So directly I am replacing that one with c. So which is equals to c by 2. Here what we have is pi. Here pi square is there. This comes to the outside and it will becomes pi. Pi will be cancelled. So c by 2 square root of m by a whole square plus n by b whole square. This is a simple equation for our cutoff frequency. Remember this cutoff frequency equation. It is very easy to remember also. This will be very much useful for solving the problems. Fc is equals to c by 2 square root of m by a whole square plus n by b whole square. From this one we can obtain the cutoff wavelength also. So what is the cutoff wavelength? Lambda c. Cutoff wavelength lambda c is equals to c by fc. So c by fc, just if you rearrange this equation, what you will get is 2ab divided by square root of m square b square plus n square a square. Just a rearrangement of the above equation, nothing more than that. So the cutoff frequency equation is that one. Cutoff wavelength equation is this one. Clearly for every mode, I am not saying that every wave, for every mode different cutoff frequencies will be there. Clearly observe the cutoff frequency is purely depend upon m and n, the mode number. The cutoff frequency is also depending on the dimensions of our rectangular waveguide A and B. So if we are varying the dimensions of our rectangular waveguide, the cutoff frequency will vary. And if we are varying the type of wave, then also the cutoff frequency will vary. So what we have to do is just we have to observe what are different possible modes which can be transmitted. Among all those, which one will have a least cutoff frequency or highest cutoff frequency, or the highest cutoff wavelength or least cutoff wavelength, like that we can examine that one. But you need to remember that the cutoff frequency is purely depend upon the dimensions of the waveguide as well as the mode which is traveling. Cutoff wavelength also the dimensions of the waveguide and the mode which is traveling. Now just we will have a brief, very small parameters that what we have, same as our wave propagation. Here also we have phase velocity, group velocity, and apart from that we have guide wavelength, free space wavelength and cutoff wavelength. Already we know the free space wavelength, that is simply the wavelength, and the guide wavelength we have, and directly I will give the relation between the guide wavelength, free space wavelength and cutoff wavelength. So try to remember that one. The guide wavelength is represented with lambda g, that this g suffix for guide wavelength, and we have a relation between lambda naught, that is free space wavelength, lambda c, cutoff wavelength. Between those all we have a relation like this, lambda naught divided by 1 minus, that clearly remember that this relation will gives you relation between this lambda g, lambda naught and lambda c, right? Lambda naught by lambda c whole square. If you want, you can rearrange this equation as per our requirement also. Directly remember this equation, that's enough. Similarly, how the phase velocity is defined? Phase velocity is equals to omega by beta. It is the definition that what we have. And for this one, for this beta we have a solution. That already we have gamma square is equals to, or gamma is equals to under square root of m pi by a whole square plus n pi by b whole square minus omega square mu epsilon. From that one, we have a simple replacement for beta. Beta is equals to square root of omega square mu epsilon minus omega c square mu epsilon. If we substitute that one here and simplify this, then we will get phase velocity as simply c divided by under square root of 1 minus, this can be written in terms of both fc or lambda c. Here I am writing the equation in terms of lambdas. So you can write down this one in terms of lambdas as lambda naught by lambda c whole square. Here also, just instead of lambda c, we can use fc, that is 1 by fc. It is also c by lambda naught we can use. You can use either f or lambda here also. This is the relation for phase velocity. And what is group velocity? Group velocity is equals to d omega by d beta. What is the velocity of the combined or the group of waves here? So after getting this d omega by d beta and a little mathematical manipulation, we will have a relation between this Vg and Vp. That is the phase velocity and group velocity as Vg into Vp is equals to c square. This is the relation that what we have. If you remember this equation, easily you can calculate the phase velocity and group velocity. Just to remember this formula. So derivation of these are not at all required. So just to remember them, already we gone through all these parameters in our wave propagation. So just to remember once again here. Now what we do is just we will examine our rectangular waveguide for TE wave for its dominant mode. And what is dominant mode? And so what are the conditions for dominant mode? Later we will derive the equations for its wave impedance. As I said, there will be wave impedance for this one. This wave impedance is different for different types of waves. So we will have these two concepts now. So before that, just you observe what is dominant mode. A dominant mode is nothing but a mode which has least cutoff frequency. That the cutoff frequency for that particular mode is very less. Remember that one. So as I said, the dominant mode has least cutoff frequency or the highest cutoff wavelength also. No problem. Whatever it may be, you can consider. Least cutoff frequency corresponds to highest cutoff wavelength. So we will observe, so among all those modes that for TE wave different modes are existing. TE00 does not exist, TE01, TE10, TE11, TE20, like the different modes will exist. Among those, which one will have highest cutoff wavelength, that what I am going to examine. Before that, just you write down the equation for cutoff wavelength. Lambda c is equals to 2ab by square root of m square b square plus n square a square. Now what I do is I will analyze this cutoff wavelength for its maximum value or the least cutoff frequency also. Once again I am saying, okay, first consider TE01. For this TE01, m is equals to 0, n is equals to 1. Then lambda c for 0, 1 I am calculating, that is for TE01, which is equals to 2ab as it is divided by square root of m is equals to 0 corresponds to this entire term becomes 0, n square is 1 by a square. Simply it is equals to 2b. What is b here? B is the narrower dimension of the rectangular waveguide. Keep it aside. And the second mode I am examining is TE10. Just I will examine this one. Then lambda cutoff for 10, which is equals to the similar equation I am writing here, the same equation, 2ab by square root of, here m is equals to 1, n is equals to 0, m equals to 1 corresponds to b square will exist for us and this term will vanish. So this will become simply 2a. That is the second one. The third one I will examine for TE11. For TE11, lambda c11, which is equals to, simply it is 2ab divided by square root of a square plus b square. So there is no simplification for this one. Leave it as it is. And if we want, we can examine for another mode like TE20. I will examine for TE20 also. So lambda c20, m is equals to 2 corresponds to what? It is 2ab divided by square root of m equals to 2 square b square. 2 square b square is 4b square plus 0. Right? b will be cancelled. This will becomes just a by. If you are examining all these values, 2b is less than 2a, as a is the broader dimension and b is the narrower dimension, always this 2b is less than 2a, and this value is very much less than these two. As the denominator is very more, definitely this is less than 2b and 2a, and a by 2 is less than 2b, 2a and this one. Right? Clearly, if you are observing, the cutoff wavelength for TE10 is the greater value than all these things. So if you write down the relation, the cutoff frequency for here, the cutoff frequency TE10 is greater than, clearly you can say that TE01, which is greater than this TE11. TE11 which is greater than TE, and what is the last mode that we have examined? TE20. And further higher are there all the modes, the cutoff wavelength, it's not the frequency, cutoff wavelength is, it's very less, right? So if you examine, obviously this TE10 mode only will have very highest cutoff wavelength or the least cutoff frequency. So that's why this is said to be the dominant mode. Clearly, once again remember that the mode which has the highest cutoff wavelength among all these, 2A is only the highest value. That's why this particular mode TE10 is said to be the dominant mode. And the remaining all modes are degenerate modes. Degenerate modes means the mode which has similar cutoff wavelength with the, or the frequency with the adjacent mode or any other mode, that is called as the degenerate mode. Now for this particular mode will gives us the maximum efficiency while the wave is traveling in the rectangular waveguide. So what they do is they will try to get the maximum efficient mode, or the dominant mode in a rectangular waveguide while they are conducting the experiments, or while the wave is propagating in the rectangular waveguide. They will ensure that the wave is propagating in TE10 mode. So this is simply the dominant mode analysis in our rectangular waveguides for TE waves. Now we will discuss about the wave impedance of our TE wave. As I said, the wave impedance is purely dependent upon the type of wave. It's not depending on the medium. So here clearly it's dependent upon the type of wave. So for TE wave, what is the wave impedance? As I recollect the characteristic impedance, or recollect the impedance in our wave propagation also, that's purely, it is the ratio of the electric field which is existing to the magnetic field. So for TE wave, simply this is also defined as ZTE, that is the wave impedance is equals to the existing electric magnitude, that what I am considering, Ex divided by Hy, this what I am considering for its dominant mode, Ex by Hy. So get the equation of Ex, substitute there, get the equation of Hy, substitute there, then what we will get is here omega mu divided by gamma. After substituting these equations, what we will get is omega mu by gamma. Now what I assume is that this wave has zero attenuation. That for our simplification analysis, I will assume that the alpha is equals to 0, which corresponds to omega mu by, as I am considering only magnitude, this will becomes beta, omega mu by beta. Now already we have a simplified equation for beta. I will substitute there, which is equals to omega mu divided by, instead of beta what you can write, this is omega square mu epsilon minus omega c square mu epsilon. So this is omega mu by omega square mu epsilon minus omega c square mu epsilon. Take omega common from this one, mu epsilon also common from this one, and after that simple manipulation, what we will get here is square root of mu by epsilon. So this is a term under 1 divided by 1 minus, here what we will get is this 1 divided by 1 minus omega c by omega whole square. This is the term which is left for us. Square root of mu by epsilon, just recollect the concept that what we have in our wave propagation, mu by epsilon is nothing but it's a free space impedance, if it is free space, or the impedance of our medium. This can be intrinsic impedance of the medium. This can be replaced with eta divided by square root of 1 minus omega c by omega. This can be written as simply fc by f whole square. Or else the same can be written as, this f is nothing but f naught, the free space frequency, or the same can be written as in terms of lambda. This can be written as 1 minus, this is lambda naught by lambda c whole square. This is also the equation that what is useful for calculation of, or the here it is wave impedance. So for calculation of ZTE, either you can use this equation or this equation. Always this ZTE is greater than eta. So this ZT is greater than eta. Why it is greater than eta? Since our lambda naught is always less than lambda c, this is greater than eta. That what you are supposed to remember. These are the characteristics of our transverse electric wave. That for the transverse electric wave, once again recap what we did. We derived the equations, later we obtained different parameters, and we analyzed all those parameters for different modes. A similar type of analysis will be there for TM wave also. So instead of going for all those equations, what I do is just I will give you the comparison between TE waves and TM waves directly. I will write them on the board. Now what I do is, instead of deriving all those equations for our TM wave, just I will give you the comparison between TE and TM waves so that you can easily remember. The measure formulas are same, the cutoff frequency formula is same, cutoff wavelength formula is same. A few parameters will change, right? So starting with the basic concepts of TE. Just for TE, how you will define TE, transverse electric wave, that there will be no electric field component in the direction of wave propagation, that is Ez is equals to 0 and Hz is not equals to 0, that is for TE wave. Exactly opposite to this one, there will be no magnetic field component along the direction of wave propagation. So Hz is equals to 0, we are supposed to substitute in the general equations of Ex, Ey, Hx and Hy, solve them. And here Ez is not equals to 0. So substitute Ez and differentiate that one according to the requirement. So these are the basic conditions for our TE wave and TM wave. And then, so what is the equation of our cutoff frequency? Fc is equals to, what is the equation there? It is c by 2 square root of m by a whole square plus n by b whole square. That it is dependent upon the broader dimension, narrower dimension as well as their mode numbers. Here also the same equation will be there. Fc is equals to c by 2 square root of m by a whole square plus n by b whole square. The corresponding cutoff wavelength also will be there. The lambda c is also same. And what are different modes which are existing for this one? For this one, the modes which are existing are starting from TE01, TE10, TE11 and etc. That TE00 mode does not exist for our transverse electric wave. And if you analyze our TM wave, for TM wave, directly remember that. And if you go for the analysis also, you will get the same. For TM wave, that the modes which are existing are starting from TM11. That prior to that, TM00, TM01, TM10 will vanish. Clearly remember that point. Those three modes will not exist for rectangular waveguides. For a TM wave, TM11 is the least mode. From that one, the remaining all TM20, TM02 or TM12, like that, different modes will exist for our magnetic wave, TM wave, right? So these are the modes which are existing. And what is the dominant mode here? The dominant mode is TE10 is dominant. That this will have the highest cutoff wavelength or the least cutoff frequency. Here the TM11 is the dominant. The dominant mode in our rectangular waveguide for TM wave is TM11. And what is the wave impedance here? The wave impedance for our TE wave, eta TE, that what I am writing, or you can write that one as ZTE also, no problem, which is equals to eta. Eta is nothing but the characteristic impedance or the intrinsic impedance of the medium or free space that what we have, divided by 1 minus the equation that what we have is there, Fc by F naught whole square or lambda naught by lambda c whole square. That is the equation that which is meant for our TE wave. A similar type of equation will be there for our TM wave also, that is eta Tm or ZTM also, no problem. Eta Tm, which is equals to, simply this will be multiplied here, square root of 1 minus, so Fc by F naught whole square or lambda naught by lambda c whole square. That what you can write. So clearly, if you remember a comparison between this TE wave and TM wave, that will be enough for us. So go for the analysis of TE wave, and based on this one, remember our TM waves. And you need to observe which component is existing. If Ez is existing, that is TM wave. If Hz is existing, that is TE wave. And most of the parameters are same to us. So this is about our TE wave and TM wave. And the third one is TEM wave. That the transverse electromagnetic wave. Just you observe the equations of Ex, Ey, Hx and Hy. And let me know, so whether the TEM wave will exist or not, right? Just for that, just go for the analysis. That's a very simple point. You are supposed to remember whether the TEM wave will exist or not. You are supposed to examine first, right? For that, let us consider the equations of Ex, Ey, Hx and Hy for our general rectangular waveguide. So I am not mentioning the type of wave here. This Ex will be in terms of Ez and Hz, Ey will be in terms of Ez and Hz, Hx will be in terms of Hz and Ez, Hy will be in terms of Hz and Ez. What is TEM wave? TEM wave stands for transverse electromagnetic wave, that the both electric field and magnetic field are transverse to the direction of wave propagation. Blindly remember, perpendicular. The electric field is perpendicular to the direction of wave propagation. The magnetic field is also perpendicular to the direction of wave propagation. Then clearly there will be no electric field and magnetic field in the direction of wave propagation. If there are no electric field and magnetic field in the direction of wave propagation for TEM wave, what about Ez? 0. What about Hz? This is also equals to 0. Now substitute Ez is equals to Hz is equals to 0 in these 4 equations. If you are substituting these 4 equations, you will get 0. So simply Ex, Ey, Hx and Hy will be vanished for our TEM wave in a rectangular waveguide. I am not talking about any other waveguide. In a rectangular waveguide, the Ex, Ey, Hx, Hy will be vanished, so there will be no field components. If there are no field components, what you can say? Simply TEM wave does not exist. TEM does not exist in our rectangular waveguide. This is a very simple bit that you may be asked to identify which one of the modes, following modes will not exist in our rectangular waveguide. TE, TM, TEM, all of the above. And simply you are supposed to pick the answer that TEM wave does not exist in our rectangular waveguide. So this is about all the types of waves that what we have in a rectangular waveguide. Now apart from that one, we are supposed to discuss about another simple topic called as dispersion in the waveguides. So what is dispersion in the waveguides? Just imagine a scenario that is a group of waves are traveling. When a group of waves are traveling means that different frequencies are there. For all those frequencies, if we have different phase constant, then obviously some distortion will be there at the output. Because of the distortion, the signal will be completely disturbed. This particular phenomenon is called as the dispersion. This dispersion is related to the phase constant. When different phase parameters are there for different frequencies, this distortion is called as the dispersion. So here we are supposed to observe what is the relation between the frequencies and the phase parameter that what we have. For that, consider the equation of phase constant beta. So beta is equals to, what is the equation of for beta? Omega square mu epsilon minus omega c square mu epsilon. Now take omega mu epsilon constant from this one. So omega square root of mu epsilon I am taking common. Square root of 1 minus omega c by omega whole square. So what is 1 divided by square root of mu epsilon? 1 divided by square root of mu epsilon is the velocity. So what I do is just I will write down this one as 1 divided by square root of mu epsilon under square root of, this can be written as fc by f whole square. So this can be replaced with phase velocity. So which is equals to this 1 divided by square root of mu epsilon is nothing but the wave velocity. So this can be written as omega by this, I will write this one as v naught, wave velocity square root of 1 minus fc by f whole square. So which is nothing but our beta. This is called as the dispersion relation, that for variation of the frequency you can observe that the beta will be varied. So how it is varying, that can be observed using our group velocity. So for that, what we are supposed to do is we are supposed to get the group velocity. So how the group velocity is defined? Vz is equals to, group velocity is equals to d omega by d beta, right? To get this d omega by d beta, what I do is I will try to get d beta by d omega. So for that, just try to get d beta by d omega, which is equals to d by d omega of beta. Now what is the relation between the phase velocity and beta? Already we have a relation between phase velocity and beta. Phase velocity is equals to omega by beta. Therefore beta is equals to omega by phase velocity. So what I do is I will replace this beta with omega by phase velocity, which is equals to d by d omega of omega by phase velocity. Now try to get the differentiation of this one. So simply d beta by d omega is equals to, so this is a function like x by y, right? So which is equals to 1 by phase velocity d omega by d omega minus 1 by phase velocity square omega d phase velocity by d omega. So this is the equation that what we have for our d beta by d omega. Now swap this one. So just invert this one. If you are inverting this one, then what we will get is d beta by d omega, which is d omega by d beta, which is nothing but the group velocity. So I'll write down this equation now. So Vz is equals to, group velocity is equals to, opposite of this one is nothing but 1 divided by, here what we have is nothing but just 1 by phase velocity 1 minus omega d Vp by d omega divided by phase velocity. So this is the term that what we have, right? Group velocity is equals to simply invert of this one, then 1 divided by 1 by Vp I took common, 1 minus omega by Vp dVp by d omega. Now examine this one. The group velocity is depending on variation of the phase velocity with the frequency. How the phase velocity is varying with the frequency is clearly describing how group velocity is there, that the group of waves, how the group of waves are traveling. Now purely depend upon this particular term, the dispersion will be varied. If this is constant means if it is 0, there is no variation of the phase velocity with respect to the frequency. Group velocity is constant, there is no dispersion. Clearly remember, the condition is if dVp by d omega is equals to 0, that is the phase velocity is independent of frequency, then group velocity is fixed, that there will be no distortion or dispersion of the wave. If this dVp by d omega is negative, negative means this is varying slowly, this particular term will vary slowly, then it is said to be a nominal dispersion. That is, this phase velocity is reduced when the frequency is increased. That is the negative meaning, right? Similarly, a third condition, this dVp by d omega is positive. If the frequency is varying, the phase velocity is rapidly varying, then the dispersion is very, very high. So these three conditions that what we are supposed to remember, and all are purely depend upon this dVp by d omega, that dVp by d omega is equals to 0. Is equals to 0 means there is no dispersion, is negative means nominal dispersion, is positive is very, very high or anomalous dispersion. So these are the dispersion conditions for our rectangular waveguides, and purely depend upon these conditions you can observe, so whether it is a highly dispersive or a nominal dispersive or zero dispersive propagation.